Thanks. So this will be the try to share the stuff that worked for me to understand. So talking about Mamba, it's preceded by S4, which was the concept of a state space model. And so I learned recently about Kalman filters, and what was helpful for me, if anyone's familiar with Kalman filters, is like, if you imagine you've got like asteroids coming in, which was a project we did recently, you've got your model that's tracking where it thinks the object is, and it's kind of got its belief of where the object is, let's say at T-1 at the last time step. And then you take an observation of it. And so you've got like your belief of where it is, and you've got your observation, and you kind of blend those two things together to come up with your next time step observation. And your belief about it there is something that they're calling a hidden state in this model here, if I've got that right. Let me just share. Oh, can I share my screen? Is that all right?
Sure.
I think it's disabled.
Go
there.
for it.
Let's see here. Oh, it looks like it's still disabled. I think you have to click the little.
No, I just granted.
Thank you. So this was his, this was oh, I don't know if this is the right. Yeah, this is Albert Gu, I think is his name, right? This, I believe, was just a talk. I think you guys covered this. This was when he's talking about S4, which is like the predecessor, if I have got that right. And when I first looked at this, I mean, I just couldn't make any sense of it, but I understand it a little more now, where like the idea is you've got some input coming in, and you want to take that input, and you want to somehow mesh it with its kind of understanding or its hidden state or its memory or its like the stuff it previously knows. And so the idea is that you as your input, which like, let's say in the case of like a large language model, is your text that you're sending in, which would be, let's say, one-dimensional sequence of what word comes after what word. And over here, XT is your hidden state. That's kind of like, in the metaphor to the asteroids, it's like your belief of where the asteroid was in the last state. And you have to mesh them together somehow. And the way you mesh them together, since they're different dimensions, is you have these, I forget the term, it's a matrix. I think it's I'm not sure if it's the right term, is a transformation matrix. It's like basically the matrix that puts them into the same, it allows them to be added together. It makes kind of the appropriate terms connect with each other. And this model, or this equation is for a function, a continuous function. And so here you've got your first derivative, I think would be correct to put that. And so the idea is really, you're taking what you understand, and when you're taking your new information and doing some clever math stuff to get the matrices to add up. And then once you've got, this is sort of like the way it's changing, then you can take your output here, and your output is, again, taking your new input and you're taking your input and then taking your previous understanding to mix them together to get an output, which would be more like your prediction of where the asteroid is in the future, or that's your text coming out of let's say the large language model. And then all this is in the continuous space. And then what he does is, and I don't know if I have the slide right here, but he does some math where he basically says, okay, well, that's continuous, but if we want to have it in a discrete space where, like, instead of a continuous function, you want to have like exactly this token, or this step of time, this step of time. This is a derivation he does. I don't know if I could find a good frame, but going forward, he refers to those as a bar, where like going forwards, instead of it being a continuous function, this would be like the state at exactly this step in time, or exactly the next state in time. And kind of the whole purpose of all that is in this part where he kind of blends together your new information with your previous information. He's able to take, in this case, let's imagine it's like your one-dimensional input, which is your information that's like really just, like, let's say is one-dimensional, like your text coming in a row, and then expanding it into the hidden state, which is multiple dimensions. And they show 4 here, but it can be more. So let's say n dimensions. And by expanding it, you're able to do 2 things. I think it's right. You're able to capture more information, but also simplify it. And I found this was a really good visualization he did. This was by a different person. I'm not sure if we watched this, but this is a good visualization, excuse me, based on something that Albert did, or sorry, that I saw that was discussed. And so the idea was like, here you've got, you've got this model going on here, and this involves a second order derivative because it's accelerating, and that's more computationally expensive. And so by taking that, and we can kind of conceptually see what's happening here, with this unit circle sine function going on here. And by doing that, you're able to expand it from 1 dimension only up and down into 2 dimensions. And by doing that, the kind of, I guess, the understanding of it doesn't involve a second derivative anymore. And you're able to extract more useful features from that. And my understanding is like that's kind of a good analogy for how you can extract into this hidden state space. And then in here is where the learning happens. And here it can extract features and get, understanding and learn things. And then of course you want to get information out. And so there's another equation that's this one here. And again, oh yeah, sorry, these are the two equations. This is the discretized input where you're taking this now, instead of being a function, this is the current step, and this is the previous step, k-1, like the previous frame, let's say, or previous token. And you're taking the previous understanding from the previous state space one moment ago, and you're multiplying it by a bar, and you're taking your current input, like I guess it would be, I'm not sure if it's the current token or the current text that's coming in. And by multiplying it by b bar, they're kind of in the same realm, and they become these blue lines here in multiple different dimensions. And then you can do the reverse and kind of extract them out and get them back into one dimension. So this is like your one-dimensional input, which maybe is your text input. Then you're converting them to a state space with higher dimensions so you can extract more interesting features. And then this here is the output, which is back to, let's say, for one dimension. Might be a good place to stop to see if I've messed some of that up or if there's like questions about that.
That's
great. My microphone off that whole time.
Yeah.
So this is S4, and that was, the past. And then what he came up with more recently, S6, was he took one thing called Hippo, which they, cutely call Hungry Hippos, or H3. And my understanding of that is that the motivation was, the motivation is, can you, using the hidden state, can you reconstruct what the input was without looking at it? Was the motivation behind it. I don't know why that motivates to what they got to, but the idea was whoever did Hungry Hippos came up with that, like you've got these different letters, these different matrices, and hold on, if I can find them again. They've got A, B, C, D, all these different matrices, and these matrices, let's say, are big and they've got lots of numbers in them. But if you could somehow take this big matrix and cleverly collapse all the information just into the diagonals like that, then it would be much, much easier to work with. And so, doing some clever math, I don't understand. My understanding is that Hippo was able to do that. And that makes things much more computationally efficient. And so like the things about S6 that were like an improvement were that. And then additionally, you've got these different matrices. And the idea was, instead of having kind of a uniform C, A, or B, each token kind of gets its own individual C, A, or B that kind of like identifies it. And then when you do, when it does what it does, each word has its own individual, like custom matrix that's for it. And then it did this thing, which they oddly didn't use the word attention. They used like every word but attention. I think it was selection. So they do their own little selection thing, which instead of attention, which does the same, at the end of the day, high level, same thing. It like figures kind of a relationship between the words. It can select which word to look at. Like, for example, if it's sentences, words that are maybe nouns and verbs will get a higher selection attention. Just don't say attention, but like it'll focus on those more and be able to look at the places where those are. I think it's probably the end of where I can have anything useful to say.
Okay. Any questions?
Do you want to sync that up with what we've been talking about?
Yeah. So that was awesome, Jason. Thanks for doing that.
Thank you.
So if you guys are cool with it, then I will share my screen and I will try not to repeat what Jason said, but just kind of like link to it. Okay. So we read the abstract. We've done this overview, which I'm going to skip for now and try to just kind of go through the same things that Jason talked about. So here's your state space model. And if you're familiar with like a Markov process, okay, you can have a number of states. Let's say, whatever a tic-tac-toe board has, 1,000 states or something like that, right? And every action you take, you do a transition to a new state. And so you can think of that as, given your hidden state. And by the way, it's a little confusing because in the S4 paper, the hidden state is called X. And then in the Mamba paper, they switched to calling the hidden state H, which is much more common in machine learning where like, you know, RNNs and stuff, we talk about it being H. But so in the S4 paper, it's still called X at the time. All right. And so if you had a simple Markov decision process, then basically your new state might be a function of your old state. But like Jason said, something a little bit more complicated, you need a little more power than just based on what state you're in. So like a Kalman filter, what we're using now is we're using the first derivative of the state, not just the state itself. So that's going to give us a little more power. And the other thing we're going to do is that in these equations, think of the input u as being one-dimensional. So it's just a floating point number. Okay, maybe it's bounded, maybe it's between -1 and 1, whatever, I don't know. But it's just a single floating point number. And exactly what he said, we're going to power it up by having our hidden state be higher dimensional than our input. So maybe it's 4, maybe it's 8, maybe it's 100. Okay, and that's going to also give us more power. So even though our input u is one-dimensional, this b is going to be n-dimensional. And so it's going to convert this one-dimensional input into an n-dimensional thing. And our hidden state is already n-dimensional, so the A matrix is actually going to be n by n. It's going to allow interactions between the individual different n, hidden state elements. And so with this, it's a linear equation. It's a linear differential, ordinary differential equation. It's going to give us a lot more expressivity than, say, if we had a linear equation only in x instead of in the first derivative. And just like Jason said, if you take this equation number 1, which tells you how the hidden state changes over time, okay, then if I know what the derivative is, and I want to know what's going to happen 1/30th of a second later, I can just integrate this function from 0 to 1/30th. And I will have my answer. So if this function had simply been like the derivative equals 2x, you integrate that, what you learn in calculus, the integral is x squared. And so if you integrate that from 0 to 1/30th, x squared, whatever, 1/30th squared, that's 1/900th or whatever, okay? So the idea is that whatever this equation is, you can integrate it and you'll get a new equation. And what that new equation will be is it'll be equation 4. It'll be a linear equation where it says 1/30th of a second later, x is going to be some complex formula times the previous hidden state plus some complex formula times the input. And because of the similar structure, we give them similar looking names, A bar and B bar, but these are completely different, expressions that you get just simply by calculating the integral of equation 1. All right, any questions so far? All right, so then the next thing we can do with S4 that we're actually not going to wind up using in Mamba is if you knew your input was exactly 30, I use a different number, 200 time steps long, okay? Then using equation 4, you can say from x0, the initial value, I can calculate x1 simply by multiplying by A bar and adding B bar times the input. But what about the second time step? I can take that thing and multiply it by A bar, and then add another B bar times my second input. What about the third thing? Well, I multiply the one I just got by A bar again, and add B bar times the next input. And if you just write out this long thing, what you will get is this like length 200 expression that has something that has like a to the 200th power plus something times a to the 199th power plus something that's a to the 198th, blah, blah, blah. You're just unrolling this. In programming, if you're familiar with unrolling a for loop, if you have something that says for I equals 1 to 10, you can do it as a loop, but you could just sort of manually figure out what each of the steps would be and hard code them for values 1 through 10, and you don't have to actually have a loop. That's basically what equation 6 is doing, is it's saying I just unrolled and hard coded what all the values would be. It may be kind of expensive to figure out what these things are, but you can unroll it and you can hard code what those values are. So we're not going to go into too much because we're not actually doing S4 here. But the nice thing about S4 is because you can unroll and pre-calculate it, it meant that either equation 4 or equation 6 could be relatively fast to compute at runtime. Equation 4 is a framework where if you input one input at a time, you get the next thing. And this works really well at inference time because you input the next word in the sentence, the next token, and it updates the hidden state, and then you get the next token, and it updates the hidden state, and so on and so forth. Equation 4 is not so great for training because what we like to do in our language models is we give it a big long thing of like 4,000 tokens, and we want to be able to calculate the gradients at all 4,000 positions in parallel. Can't do that really great with equation 4, but the wonderful thing is equation 6, once you've unrolled it, let's say you unrolled it 4,000 times, you can actually calculate the gradients on all 4,000 positions in parallel. So people love equation 6 for when you're training the model. And that's why S4 was really promising, because it's fast using equation 4 at inference time, fast using equation 6 at training time. So then they use this and they train it on things. And I'm going to use the example of like an echocardiogram. You know, you're looking at the signal of somebody's heart, and it worked really well. But somehow when they decided to use this for language models, it didn't work as well. And this may not be like really good formal math, but like my sort of high level intuition is, if you think about an echocardiogram, obviously, at different times, you're in different parts of the cycle of the heart beating, okay? And so the model needs to be expressive enough that it can understand that I've got a sequence of inputs, and at one part, it's, it's like the left atrium is beating or whatever, and then in a later time, it's the left ventricle beating. And so there's different parts, and you should relate to them all differently. But when you see the thing, you can kind of relate to every heartbeat, that full cycle, as being the exact same thing over and over and over again. It's a little bit of an oversimplification, but that's kind of like the intuition I have. However, in language, you could have one sentence which is way more important than the next sentence. You could have one sentence that's really setting the mood, one sentence that's setting the subject, one sentence that's giving you parenthetical information that's really totally unimportant. You can almost forget about it, right? So this is a case where language models are harder. That's the intuition I have. It's harder. So unlike just the idea of an echocardiogram, what you want now is to know not just where am I in time in my sequence, but like contextually, give me some more metadata about what's going on with at any particular input word, okay? And so then practically speaking, how do you do that from a computation point of view is you say, okay, I had A, B, C, and delta in S4. If instead of having them trained and then just having these 4 values, they're matrices, they're not like scalars, but just these 4 values, exactly what Jason said. If I now say, when you see the word bank, I'm going to use a particular set of these. But when you see the word tree, I'm going to use a completely different set of these. And when you see the word David, I'm going to use a different set of these. That allows you to then bake in a lot of like contextual information about nouns, verbs, subjects, whatever, into it. Exactly how it's working, I mean, we don't know exactly how transformers work. We don't necessarily know how, Mamba works, but that's this selectivity or attention, if you will, this way of saying I'm going to bake in variable interpretation depending on what the input is. So it's giving it even more expressivity. And this is the kind of expressivity that our current transformer language models have. So you embed each word into a vector, and that's a one-time thing. Every time you see the word bank, it's going to be the same thing. But the way the attention mechanism works is you embed it as a key, it's always going to give you the exact same key vectors. But depending on the other words, when they do their query vectors, you can get completely different results based on any pair of words. And so you get a little bit more of this power in Mamba because now, instead of having, again, the same B, C, and delta all the time on every single input token, you can say, in the case of dog and fur, they may have particular weights that do things that dog and cloud just don't interact in the same way. That may not be like completely mathematically correct, but that's sort of my high level intuition.
Hey, Ted.
Yeah.
So it's just the BC and delta matrix that are allowed to vary, right? So
yeah, I mean, it's 3 out of the 4, so it's...
Yeah, but isn't it the 4, I don't have the picture in front of me, but isn't it the A matrix that takes the prior hidden state, and maps it forward?
Yeah, so what happens is the A matrix in the continuous time is very important here, but there's also the B.
Yeah.
So your next hidden state is going to be based on both A bar and B bar. Both of these, A bar and B bar, are dependent on B. So in fact, you will get a different A bar and a different B bar at every time step. So even though we don't vary, A based on the input token, you are still actually in de facto varying your A bar and your B bar at each.
Oh, interesting. Okay.
A bar, A happens not to be changing. B, C, and delta, which is not on here because it's not part of S4. They do vary based on your input. They do not vary based on your hidden state. So if for some reason Mamba were not expressive enough, the next leap would be to say, I'm going to allow these things to vary not only based on my input, which on this slide is U. I'm going to allow it to vary based on my X. Now you've got crazy degrees of freedom because now you're saying you can pretty much, the only limitation is that it's linear because I'm basically allowing it to vary both on my input and my state. It's, you know.
And is the reason they didn't do that just because of the, like, yes, you like massively increase the expressivity, but you're also massively increasing the dimensionality of the training. Is that?
Can I say something?
Please.
So if you do that, then you basically are going to have an LSTM and you're going to have the backpropagation through time problem, if you think about it.
Yes. So as far as I know, there is no trick for speeding up if you're going to make it. You probably can do it, but I think ideally, yes, you want sort of the simplest possible model that gives you enough expressivity to solve your problem. I'm not sure if backpropagation through time is a problem because Mamba is doing backpropagation through time as far as I can tell. It's just doing it on a GPU pretty fast.
Doesn't the fact that it's also using Legendre polynomials to do it also change that propagation? I don't know the math well enough.
I have lost whether there's formally Legendre polynomials in here or just the idea that because Legendre polynomials can span whatever, that that the model could learn representations that are akin to that,
As
that would
complex.
allow it, but it's not that we're explicitly coding in Legendre polynomials.
Meaning that it's the intuition / insight versus the mechanism.
Yeah, I think, but I'm not 100% sure.
Hey, Ted,
So-
you mentioned that the C matrix is one that can be changed up, but
Yes.
doesn't, based on the page we're looking at right now, isn't that C matrix being multiplied on the hidden state, xt?
It is, but the hidden, the what C you choose depends only on you. It does not depend on X itself.
The
Gotcha.
selectivity. Yeah.
Okay.
So there's C sub dog, C sub tree, C sub cloud, but there's not C sub dog, comma, hidden state 1, C sub dog, comma, hidden state 2. That makes
sense.
Kira, did you have a comment there? You're not.
Okay. So then this diagram, I don't totally love this diagram, but if you're wondering how does it do the computation really fast, okay, at a given hidden state, you want to calculate the next hidden state, okay? So what you need is you need A and you need B, and you need those to go into the GPU, into the super fast, like cache, SRAM, whatever you want to call it, into the registers, and you need to do a bunch of math, and you'll calculate A bar and B bar. Once you know A bar and B bar, then you can multiply A bar by this thing here. You can add, and you need your input wherever, but anyway, so then you add, you multiply, then you add, and you're going to have your new hidden state, okay? And the thing that they do is they say, based on their CUDA kernel they wrote, do not try to write this hidden state back out to main GPU memory, because main GPU memory, so-called high-speed, high-bandwidth memory, is still really slow compared to SRAM, which is basically your cache. Keep it in the cache permanently. And that is kind of the main speed up, is by taking this object and saying never, ever, ever try and write it out. And so then A, B, C, and delta are all objects that are n by 1 or 1 by n. And so the amount of time it takes you to copy that from main GPU memory to the core is n times faster than the amount it would take you to load any n by n matrix, or L times faster than it would take you to load any L by n matrix, or anything rectangular is going to be that many times slower to load than a just 1 by n or n by 1. And so they say we can write something that will load these A, B, C, and delta things that are n by 1, 1 by n, and that is what's going to cause our thing to be slow. That is the bottleneck on the performance of this computation. If it weren't for that, it would be like another, 20 times faster. But because we have to load those, it's great. But just imagine if this took you whatever, if right now you say, hey, I can do, 10 training steps, in a minute. If you had to load an n by n, and n is 16, then basically you would go from 10 training steps to 10/16. You'd go to less than 1 per minute. And if your n is bigger than that, it's even worse. Or if it's your L, your sequence length, and your sequence length is 8,000, then you would go from doing 10 per minute to doing 1 every 800 minutes or whatever. So that's why stick with tiny things. Don't do anything rectangular back and forth between main memory and GPU.
Hey, Ted?
Yeah.
Could you cover like these XT, what the little squares in that XT stack is, and also the yellow lines or orange lines, whatever they are, that are going across? Like there's 4 little lines going across.
Yeah. So in these equations and in the nice graphs, I really like the ones that Jason chose. you think of U as a one-dimensional input.
Mhm.
Okay. When we get to the real world and we're doing actual language modeling, you don't embed words, tokens, as a single floating point number. Usually it's something pretty big, like a smallish model would be 512 for your D model. Okay. And I can't remember if GPT-3 was somewhere crazy, like around 16,000 or something like that. So the reality is U is no longer just a single value. U is a vector. So they show in this diagram X being a vector.
Okay.
Okay. And so this is a 5-dimensional vector, I believe. I don't think this is time. I think this is, yeah, this is actually a 5-dimensional vector. So imagine D model is 5. And in this case, H really should be bigger, but they're showing you the hidden state as being 4-dimensional. Because remember, we're projecting our inputs into a higher dimensional space. So these are just
That's
like
what it, yeah, I was
sample
noticing.
dimensions to show you that these are not one-dimensional objects. These are actually, many-dimensional objects.
Mhm. Yeah, I noticed that there's 4 lines up there and it says n equals 4 in the text. So that's representing then a projection. Whatever the first box of X is, it's projected into something 4 times as big. Is that what you get out of that?
Yeah, so I believe in this example, if D model were 5, then you're really going to have 5. And I think that's why this thing is instead of a whoops. Instead of a rectangle, you'll notice that H looks like a stack.
Right.
And so this is really supposed to be a stack of 5 length 4 vectors because xt is length 5 and we're expanding it by a factor of 4.
Okay, that makes sense.
And you do need to do similar things with these other guys. So maybe when I said they're 1 by n, well, now it's going to be 5 by n because our model D is 5 or whatever. But again, whatever this is, you don't want to increase its size by another dimension. So keep it as small as possible.
Mhm.
So this is the how do you do it really fast in the GPU, and then this other diagram we'll get to is just saying we're going to put it in some blocks. In the paper, they do an ablation where they just use, if you can see my mouse, they just use the blue block and they don't use any of the other stuff. And it got like 95% of the performance of this thing with everything else. So I treat this everything else as useful, but not critical to what makes Mamba tick. S6 is what makes Mamba tick. This other stuff is just like nice, but not the theoretically difference maker. So I'm not sure what we want to do next. So last session, we were looking at the Yannick video, and I do have it queued up if we want to listen a little bit more. Most of the early part that we listened to was him actually talking about S4 and explaining why S4 was really fast. He didn't really explain it the way Jason explained it, and I think he actually has a technical mistake in one place where he explains it wrong. But basically, he uses the expression zoom to say that you can do inference fast, you can do training fast. And then he's explaining some of the architectural differences between Mamba/S6 and S4. And so that's where I started to rush and was like fast forwarding through the video. But if we want, we can kind of pick up there or if you guys want to have a little bit more discussion or look at the paper before we do the video, or what do you guys want to do?
Why don't we do the video, Ted?
All right, so I think I've got it queued up to about the right spot. So Yannick has described the selection mechanism and said a little bit about, whoa, now that you let BC and delta vary, this is going to break the way it used to do zoom. I think this is where he made the mistake and he said, but there's a new Zoom. There actually isn't a new Zoom. There's no free lunch. It's just that we programmed a CUDA kernel that does it really fast. But the running time is still like n squared or whatever. It's something not nice. It's just we're not doing it naively. We're doing it super efficiently.
All prior SSM models must be time and input invariant in order to be computationally efficient. We overcome this with a hardware-aware algorithm that computes the model recurrently with a scan instead of a convolution. So they say essentially we sort of make it really fast on GPU, even though we have an algorithmically a different algorithm. We need to compute something, making the actual recurrence, or actually recurrently, but we do it in a way that fits really well onto GPUs, and therefore it's actually in the end it's actually faster. And yeah, they make this into a model called Mamba. Mamba is not the same as selective state spaces. Selective state space are a part of Mamba, and then combined with some other stuff like 1D convolutions and up projections and gating, that becomes the Mamba architecture. It's attention free. Therefore, it avoids the quadratic bottlenecks of attention-based models such as transformers. So they say these are fully recurrent models with the key property, for example, high quality. Selectivity brings strong performance and on dense modalities such as language and genomics. I think that's going to be the biggest sticking points. So they have recognized that, this super scalable thing like S4 is not really suitable for language because you need to be a little bit data dependent in your transitions from, through the hidden states. And now they say, well, selectivity brings strong performance, which, because they added selectivity, they added this dependence on the input of the transition, now gives them a bump in performance. The jury's still out whether in the future they'll say, yeah, it's better, but still, in order to really reach the performance of transformers, we also need to make that transition actually dependent on the hidden state. And at that point, we're back to essentially LSTMs. But it could be that the dependence on the input, just the input, already makes them as strong as transformers on a lot of important benchmarks. Fast training and inference. Computation memory scales linearly in sequence length during training, and unrolling the model autoregressively during inference requires only constant time per step, since it does not require a cache of previous elements. So there's no key value cache, and so like in transformers, you literally just have to remember the last hidden state, and then producing one additional token during inference is just, it's just...
Our mission in Coding Dojo is about redefining what's possible in our students' lives. If you are...
Sorry.
2 matrix multiplications or something like this, right? So no attention, no nothing, just multiply it in and you have it. And long context, the quality and efficiency together yielded performance improvements on real data up to sequence length 1 million. All right, so this is...
All right, so briefly, what he's saying is, at inference time, we just need one input. We calculate our A bars and B bars, and we calculate our new state, and we also calculate our output Y. Okay. Yeah, you're also calculating C bar and D bar, but those usually are not the part you're worried about. So it's constant time. It's order 1, if you're familiar with the big O notation, for inference. For training, this is where the model is order N, or sorry, order L. It's linear time in how long your sequence is, because as far as I understand it, you are still doing back propagation through time. So if you have L tokens, I'll just use a number instead of L. If you have 100 tokens, then basically what you're going to do is you're going to go one step backwards from the 100th token to the 99th token. And fine, you'll have your whatever, your A bar and B bar, and from that you can backprop into your A and B from there. But you still need to repeat this whole process to get to 98 and then 97 and then 96. And so you are going to be backpropping through time to get all the way to your, first A bar, B bar, and your first A and B. The thing that they do that is not the naive calculation is in the naive calculation, when you use autograd in, say, PyTorch, it's going to do the computation graph, and it's going to save things off so that it can do the reverse mode differentiation. In this case, they do not use autograd. They use a manual calculation that keeps these H's in memory. And so I was going from left to right, but when you're doing backprop, you go from right to left, and you never write H out of your core cache fast SRAM. You just simply say, H100, I now have H99. And then I have H99, now I have H98. And you keep doing this, and you will calculate all the H's that you need in order to do your backprop without ever having written any of them to memory. And in order to do this, you trade off not having saved anything during forward mode by doing more flops. You're actually having to redo these A bar, B bar calculations on the backward pass, okay? But everyone's willing to trade flops for wall clock speed, and that's what happens here. And that's the same thing that happens if you guys are familiar with flash attention. Flash attention is doing the exact same calculation as regular attention, but it's doing things in a different order. And if you read the paper closely, you'll see that it's actually on the GPU doing more matrix multiplies. It's repeating certain calculations. But those repetitions, I don't know exactly what it is, but let's just say a matrix multiply is 100 times faster than a memory load. So if you can trade off a few extra matrix multiplies in order to avoid loading something, you end up with much, much less wall clock time. Sorry, the hand was raised and I was trying to just finish the thought.
That was me. I have a question. I'm not an expert like you guys, but it's from the first page, I think that was the equation 5, and we are talking about that it does not depend on the previous items. The yk, it's equation number 6. Yk is equal to c a bar k. So the first question is that, does it mean the step k, it depends on a step k and k minus 1 and so on. But because we are using state space, which reminds me of control systems, and we are mapping the time direction to something else, and instead of using time, we are using velocity and position. So although we have only one, it does it really mean that we are not considering the attention, the n dimension, or we are just mapping it to another space? So we are actually considering the words behind it, maybe k, dimension of k. Was that clear?
I think so. And anybody else can free to help me.
Can you
out,
restate it?
I
followed right up
person.
until the very last sentence.
I mean that in state space control systems, that not to deal with time, we map the time direction to some other space, and because of that, we take derivatives, and x dot here is actually the velocity in the control system, and y is the position. So instead of dealing with time, which means that the steps for a sentence the attention will be a vector, the previous words. We are actually mapping all together into another dimension. So we are dealing with attention, but in a different way. How come we have faster calculation, as you were saying?
Yeah. So I'm not sure if I'm going to answer your question correctly. Okay. So let me give you the answer that I think explains what you're asking, but then tell me if I totally missed. Okay. So the really kind of cool thing about these real continuous time equations 1 and 2, okay, is that 4 and 5 are not different equations. They are basically the exact same equation 1 and 2, but we've just mathematically rewritten them in a way that, let's say my delta t is a 30th of a second, that this equation 4 will give me the exact same answer after 1/30th of a second as this equation 1 would give me if in continuous time I just let it run for a 30th of a second. Okay, and then this bottom equation 6 gives me the exact same answer. Like if we had infinite precision floating point, they would be the exact same answer. This is not an approximation. This is not an intuition. This is the exact same mathematical quantity. Okay, so what equation 6 is telling you is that any length 200 input, you are going to multiply all of your inputs, U0, U1, up through U200, by predetermined constants. That's pretty wild, okay? But so what it means is that those constants have to have a whole lot of expressivity baked into them. So like, I'm imagining like if you had a little kid and you were playing a game and you said basically like, okay, you're going to like pick a card from a deck of cards, okay, and based on the number of the card that you have and the word I shout out, you're going to take a step in a particular direction. So if you're holding a 4 and I shout dog, you're going to move 1 step north. If you're holding a 4 and I shout cat, you're going to move 1 step east. Okay? I'm just making up this very made up game. And if you have a 3, you're going to do this, you're going to do that, right? Clearly, the rules of the game are predefined. Okay? And what this is saying is that no, you're not going to do the exact same thing on step 200, no matter what words I shout. But I can come up with a set of numbers that encapsulate that if these are the 200 words that I shout, you don't need to use different constants to multiply by all of them to figure out what I'm doing. You just need this right set of numbers such that the first 199 basically encode what your state is. And then you just need the last word that I shout to know, oh, okay, they're holding a 4. I shouted dog. So now you're going to go 1 step north. So it's a pretty cool system that now you need to learn these really, really good hidden representations. But if you can learn the perfect hidden representations, then what we're saying is you have linear dynamics on these hidden representations. And when you combine linear functions, you just get a new linear function. So, right, if you say y equals 2x plus 3w and y equals whatever, 1/2 x plus 9w, no matter how many linear equations you have, you can always just add them up and you'll just get some new constant times x plus some new constant times w. And that's effectively what they've done here, is they've just unrolled it.
Can I answer a second half of that question too? Which I think there's the 2 portions, right? Like there's the one portion which is doing the unrolling using discretization ahead, which is what Ted just described. And that basically simplifies a lot of the math versus control theory, where you have to constantly be computing that. The second thing that Ted mentioned, which I don't know if you're as interested in, is just the computational methodology. And by using this is the last thing that Ted was talking about, by being aware that GPUs are fundamentally limited by flops once you have the memory loaded. Even if you're computing 1,000 times more, If you're doing it in a single flop, you end up being in elapsed time much faster. And so they're trading off on the margin here, and it looks like pretty reasonably that they're doing more computation, but they're doing it in such a way that they're doing it in a single flop, which if you have a 1 gigahertz clocked GPU, whether you're doing one matrix multiplication or you're doing 1,000 of them, depending on how many compute units you have, it takes exactly the same amount of time.
Right. That was the thing. I was thinking that the number of computation might be more, and like, yeah. Please go ahead.
Hey,
Yeah,
Jen.
and
Whoops, sorry.
let me just say one more thing on this thread of this question. So now remember, this slide shows S4. We are no longer using S4. So equation 4 sort of still holds. It's just that A bar and B bar are different at each time step depending on what your input is. So there's an A bar for dog, and there's an A bar for cat, and there's an A bar for tree, and A bar for cloud, okay? And because we do that, that completely violates the assumptions, and equation 6 does not work. If you listen to the video from the last 2 weeks, I've been joking that I'm guessing that Albert Gu spent 6 months of his life that he's never going to get back trying to figure out some super clever math that lets him do not exactly equation 6, but something similar that's like really cool that cuts down on the amount of computation, and eventually hit the wall and could not come up with any fancy math that says, if I let A bar and B bar vary on each input, but I constrain them in this particular way, then like there's this clever math I can do. And I'm guessing, who knows, right? But I'm guessing there's 6 months of life that he's not going to get back because he tried that and he couldn't make it work. And so then he like called up his buddy Tree from Stanford, and it's just like, I can't make this any fewer computations, but can you just make it run fast as hell? And Tree's like, yeah, I got this, bud. And so then it's like, okay, this thing is still, for a length 2000 thing, it's doing a whole lot of computations, but they happen really quickly, so nobody minds. I don't know if that's really what happened, but that's like the cartoon that I have in my head.
Can I ask one more question?
Yeah.
And in the higher level, out of the scope of math, in which part of generative AI you think this method is better than transformers? Do you think, just my speculation, do you think it will be less effective in creative content?
So I think it might be in the video, and I don't know if I have a good diagram for it, but basically there's this analogy that if you look at an RNN, a very simple RNN, it has a fixed hidden state size. And as you get longer and longer sequences, the problem you have is that you're trying to compress information about everything that you've seen so far into this fixed length vector, okay? And it's just really hard to do that, And so then the transformer is the other extreme. The transformer actually has no state, so to speak, literally, okay? On every time step, you just do this attention calculation on every single token that came before you. So for each new token, you're re-looking at every input you've ever seen. So you're not storing any hidden state. You're just using like full brute force to say, okay, pull back up everything I've ever seen, and I'm going to see if any of those are important. And the important ones I'm going to, attend to heavily, right? And then you get the next token, and it's like, well, this is token 201. Are you remembering that like you're in French mode and that you're talking about whatever? Like, no, I'm just going to pull all 200 previous tokens all over again from scratch and calculate attention on them to see like what's important right now, right? So that's the two extremes of the trade-off. One is super fast because it's constant time at inference and training or whatever, and this sucker is quadratic because the calculation it's doing is looking at everything. So the holy grail is you do something in between that's not quite quadratic. And that's what Mamba's trying to do, is it's trying to say, I have a hidden state. The hidden state of an RNN wasn't quite smart enough to pack stuff in there using this very fixed form, using an LSTM, whatever. I have this other form that has some restrictions on it. There's restrictions on what the A matrix can look like, restrictions on this and that and that. But I will let this vary on each input based on the input, based on the, if it's dog or it's cat or it's whatever. And the hope is that that will. So that was my very long-winded way of saying, in theory, you can beat attention because dot product with queries and keys may not give you every possible level of expressive power, but you can't beat the fact that attention gets to cheat and look at every word that's ever come before. You can't fundamentally beat that phenomenon.
And so I would kind of jump specifically in the kind of colloquial of generative algorithms. I think the two problems that Ted's describing that I think a lot of people could wrap their heads around would be hallucination. So the goal would be that if you can store some compressed version, let me use like the most obvious hallucination of the six-handed person, and you're storing, instead of all the pixels of every hand and every little bit of that, you're storing a hidden state that says I'm 1, 2, 3, 4, 5 fingers, we're done. And an RNN is not going to be smart enough to know I need to count freaking fingers all the time, because it just has too small a limited of a memory. And so you want to have some form of a generalized memory, not too detailed and not too generalized. And the goal of this, I think, is to come up with something in the middle that's mathematically tractable. The second problem is overly complex sentences. So if you've used a lot of generative systems and tested them, you'll notice that the ability to have attention means that the sentence always flows, but it doesn't always make sense. And it doesn't always make sense in context. And so and if you do a generative, like a generative image specifically, frequently it's only able to hang on to certain words because it doesn't generalize very well. And so if you type in, I want to have a picture of this dwarf and Snow White standing on the Eiffel Tower eating biscuits with a stormtrooper, it's going to get 2 or 3 of those concepts precisely right, which is exactly what a transformer will do. And it's going to totally bugger up half of them. And so, and sorry, that's a more colloquial version of what Ted said, in case that's helpful to you.
Thanks.
Roger, you had your hand up earlier.
Oh, no, that's okay.
Okay. So we can keep going with Yannick if there aren't. Oh yeah, question.
Just wanted to say that looks like there's also S5 also from Stanford, and they had used parallel scan as well. I don't know if it was IO efficient as well or not. Probably the IO efficient part was done by Tree, but the parallel scan was already utilized in S5, which is from the same university. I'm not sure if it's the same people. So anyway, yeah.
That's perfect. Correct. Yes. So they reference S5, saying that that's where they got the idea from the parallel scan, and then presumably Tree figured out that not only can we do the parallel scan technique, but if we keep certain things in cache in fast SRAM, then not only do we have sort of that going on, but we can reduce the wall clock waiting time, because the GPU is so dependent on how many things you're loading, not how many things you're computing.
Right.
Awesome.
Yeah. And if you refer to in the paper, section 3.3.2, that's where they refer to all these tricks, if you may, for improving the parallel scan and the on GPU performance. So they highlight, and actually show the math of at a very high level of
Yeah,
how
I-
they reduce
I
complexity.
think Yannick might be just about to talk about those. I'm not 100% sure. Let me see if that's actually exactly what he's about to cover. I mean, not in detail the way you're saying, Dave, but just he'll mention them, and then if we want, we can pause if we want to go into more detail.
The architecture is a bit distributed throughout the paper. This is the selective state space part of this. There's going to be a more extensive thing here. So the Mamba architecture consists of the part I've just shown you, but also of other things. So you have to imagine these things are going to be layered on top of one another, and then essentially you'll always consider the entire sequence as one during training. So if we go in here, this here, for example, this is a linear projection. So you project up in dimensions, and you project each token individually, like in a transformer. Then you do a 1D convolution. There is some nonlinearity in there. Then comes that SSM. Now, in these two things, you want to consider the whole sequence as one during training, right? However, in the projections right here, they, as far as I understand, go just individually over tokens like the MLPs in a transformer. And then there is also this extra mechanism right here, which is a gating mechanism like you're used to from other gated architectures. Again, this doesn't go between time steps. That's important to note. This goes from layer to layer, right? So as you go up the layers, the time would be some sort, the time steps aren't even shown here. There's no time direction in this particular diagram. There's also residual connections like that go out the way and so on. Yeah, so the Mamba is an architecture that includes this new selective state spaces. That selective state space layer looks about like this, and here we now have a time direction, right? So here we now consider how do we compute one token in this sequence, given that we have to accumulate this hidden state over time. And again, we can do this either during training, where we try to compute all of them as fast as possible, or during inference, where we just do one of these time steps. So as you can see, the backbone is just going to be, we have this, we multiply, essentially there is this A matrix right here that we're going to use, and there is the input that somehow comes in, and from these two things, we're going to produce that next hidden state. Now, what is all of this right here? All of this is part of this state space architecture. How does that look? There is a technicality in here, which is called...
Stop reading research papers like this. Googling back and forth while reading actually eats up more time.
Discretization. Now, the theory behind state space models and so
Hey,
on
Ted, you got a question?
Was developed for continuous time systems. And if you want
Is that a new question, or did you just not put your hand down from before? Okay. So I was wrong. He didn't actually talk about it. I'm trying to remember if I have a slide on this. So the three tricks, where's my mouse? So the parallel scan we talked about. So this is the S5 paper, and I think it's in the chat. I haven't been able to click on the links because then it's going to cover up my screen. But kernel fusion is just the idea that you write custom code to kind of do everything at once, instead of having like just naive, you do one thing, you write stuff out, you do the next, you load things back in, you do the next thing. And then this recomputation thing is on backprop, is where I was saying it's doing extra math, because it's recalculating A bar and B bar from scratch on the backward pass. But it's doing that in order to avoid loading things into memory that it's stored from the forward pass. So these are the three main tricks in the in this diagram that we were talking about, if that helps.
Ted, can I ask a question about this? One more question. So I'm trying to understand two things. One is the performance. So if I think about how I'm training a transformer, one of the advantages, as I recall, is that I essentially can take my entire sequence and run the calculation up through the multiple layers, and in one iteration of that depth, come up with a prediction for all of the next tokens. Right, so that makes it efficient during training. If I'm training this one, if I'm understanding, instead of doing all the tokens at once, I essentially will be going through multiple steps. So stepping through time, computing the next hidden state, the next hidden state, the next hidden state, and each one of those requires the full stack of the model. And then once I get at the end, if I'm training, I have to then back propagate the gradient step over step over step over step into all of the parameters of the model. Is that right? So it's longer to do this recursive steps, do a forward pass of the model for every time step, as opposed to the transformer where I can do them all concurrently.
Yes. So this is a form of RNN now.
Right.
It's a very fancy RNN. It's not an LSTM, it's not a GRU, but it's a kind of RNN. So that, I believe what you said is correct.
Okay.
And then there's a hand raised, so there may be a correction if there's something I don't understand. So yes, you are going to have to do things one step at a time on the forward, and then you're going to have to back prop through time on the backward.
For each token in the sequence, I have to back propagate through.
And if
so
you're really clever, there's some things you can parallelize, because like you can calculate these projections. Okay. So for each token, you can calculate what the B, delta, and C are in parallel, because that doesn't require anything. That's just a predefined function that says for dog, here's the B, C, and delta you want. For cat, here's the B, C, delta you want. And so that you can do in parallel.
I have to go through the A matrix though every time step or every sequence.
It's this hidden state calculation that's the most.
And so the magic is they just came up with a way to do that fast. So in the transformer, they did it in parallel, and that was fast and wonderful. Here, they have to do it recursively like that, but they found a way to do it really fast. Okay, so I get that.
But then also at inference time, when you're not training it, you really are only presenting one new token at a time. And so then it's super duper fast, because now it's not even linear time, it's constant time.
Yeah, I get that. Okay, so then the other
Can I add one thing, Roger, before you go on? But also because of the way that it's structured, I believe you can also do those not in parallel on one sequence, but you can parallelize multiple sequences during training. So just, you're not throwing away GPU.
A mini batch, I mean, mini batch of sequence. Okay, so Kira?
It's Vida.
Oh,
sorry. So attention, when you compute the attention matrix, it's OL squared. So if L is the length of your sequence, then L squared is the complexity of computing that attention matrix. But here it's OL. Even when you pass tokens, compute them serially. Actually, the parallel scan parallelizes it, so it's better than linear, I think, if I'm not mistaken. So that's also a difference, that here you have O of L, but then it's not, it's not free lunch. So you have these extra expansion of dimensions, like your hidden state has this extra by n dimensionality, so that makes things again more expensive. But in terms of the sequence length, attention is L squared, but here is linear or sublinear. So that's maybe I think it's relevant to the question that you asked.
Right. But just to be clear, if you take a vanilla RNN, we're not saying that that'd be the most performant because it's kind of dumb, okay? But a vanilla RNN is also order n, and we hate it because it's order n of naive operations. Sorry, n being the length of your thing. So it's important that like if you are doing a matrix multiply and then you say, oh, I need you to do 100 of them, but you can actually just specify all 100 of them at once. For all I know, like doing a, instead of a 64 by 64 matrix multiply, you do a 64 by 64 by 100 matrix multiply, right? For all I know, that takes like 3 times as long. It doesn't take 100 times as long. Once you get all the data in there, the GPU just churns through things pretty quickly. So that's the reason why you really have to kind of like understand for this. It's not just the scaling factor, it's the units of scaling. If it's, whatever, naive memory loads, blah, blah, blahs, and it's, I don't even know what the number should be, 100 microseconds, scaling linear might kill you compared to if it's, n squared and it's 1 microsecond.
So here's the second part of my question. So if I start to think about this kind of like an RNN, maybe without the nonlinearities, a little smarter RNN. The other problem I have with RNN is these vanishing gradients from these really long back propagation through time. How did we fix that problem? Because we're still doing the back propagation through time, essentially, right? We're just doing it fast.
I believe there's something in the parallel scan, isn't there, Dave? So
Yes, so
that's another trick.
That's right. If you go to, and I just copied that text, and I know Vida has hand up, and sorry to go past you, but I just copy pasted that from section D, page 28 of the paper. That's not the right paper, is it?
No.
No, I was looking at that. Oh, I had it open, and then
It's 2312. I can put the link for you if you want.
yeah, faster than if I have to redo the whatever.
I'm putting it there. Give me a second.
I think I might have the link here.
I just put it that you can press.
All right, yeah. Thank you. Much faster.
So if you go to page 28, bottom part, that's where I copied it from anyway. So
yep. And then which part of it?
Yeah, this one, speed. So the standard way to implement the scan algorithm, which is, let's say, the naive way, would be pretty memory intensive. And if you go to the last line of this paragraph, I don't know if you're, yeah, this one. We can instead fuse the discretization step, the scan, and the multiplication with C into one kernel. So they do the kernel fusion of doing the parallel scan, where instead of doing this in order L, which is the order, whatever the number of time steps is, right? They are able to parallelize it. I mean, we need to understand the parallel scan and parallel associative scan algorithm in detail to be able to understand this optimization. But that is the key to optimize it by 20 to 40 times. And in the next paragraph on next page, if the length, the sequence is huge, for sequence length L too long, we split the sequence into chunks and perform the fuse scans on each chunk, which is similar to what flash attention is, right? So, so that's how they are able to optimize the performance.
That's great. Thanks, Dave. So Roger, I think the answer is that this parallel thing, I've described it as just keep a H in memory and do your A bar, B bar, and then just unroll in time linearly, okay? They're not doing it that way, literally. They're doing something else more clever. And by shortcutting that, not only is it faster, but it has the side effect that you have fewer steps. And so I think you're going to have less floating point round off errors. Well, I mean, if it's FP32, hopefully that's good enough, but whatever, you know, it's gonna help with sort of like underflow problems. Now, I think it is still going to be true that on a super long sequence, if effectively you're not using exactly A to the sequence length power, but indirectly you're doing a version of that, right? I think you are going to get the phenomenon that the gradient is going to kind of vanish when you go that far back. But that's okay, because you're still accumulating a lot of gradients from all the more recent tokens as far as your training is concerned. So yeah, I think you're right that if you, and I may be missing something, but I think if you trained on a sequence that was 100,000 long, the gradient coming from the very first token, by the time you're at 100,000, it's got to be pretty tiny.
I know, but so I'm unsatisfied by that answer. Because this was such a fundamental issue with RNNs, though, right? I hear what you're saying, Ted. Like I think that's fair. But like, if this was like the big problem with RNNs, how can we be so quick to write it off now that we found a new RNN? I think if I were to reinterpret Roger's question, that's the way I'm thinking about the same thing.
So I think the biggest change between RNN and this implementation is the state space formulation. So RNN do not have the parallel to the state space directly, if you may. So in principle, this is an RNN principle, but the formulation is different of the hidden state and how it propagates from time step to time step.
Yeah,
Yeah, not so much the hidden state, but the propagation.
So he's got them written here side by side. I'm going to go back to my slide if you guys are okay with it.
Ted, there was some place I saw it flashed on the screen where it looked like A was decomposed into an A plus or an I plus delta or something.
That's how you calculate A bar. So
that's just
A bar is exp of delta T times A.
Yeah, because it's just the time, right? It's just conversion of continuous to discrete.
But you have to integrate. It's not just a simple. But what I was going to say is, I think we talked about this maybe 2 weeks ago. Once you've turned it into an RNN with equation 4, okay, this now is not a fancy RNN. This is literally an RNN.
Yeah.
Okay. You're just saying that the hidden state equals A times the hidden state plus B times the input. So this shouldn't do any better than a regular RNN if this were just an RNN. Okay. So for the people who are here, I don't know if you remember me saying, not all A bars and B bars are whatever allowed equally likely. You can only get A bars and B bars that respect equation 1. So the dynamics of this are controlled by equation 1, not equation 4. If you randomly initialized A bar and B bar the way we normally randomly initialize things, this thing would turn into just an ordinary RNN. It's because not all A bars and B bars are legit. It's because we use the dynamics from equation 1 to calculate the A bars and B bars of interest that we get different behavior than a regular old RNA.
If you look at the discrete formulation of the thing, there's exp, there's delta t and minus a, and all that part, creates this decaying effect. So older tokens get decayed and new tokens get added. And then if, again, the B kind of plays the opposite role of it. So, the A and B, A bar and B bar are kind of like the forget and remember thing in the LSTM. Yes. Actually, in the code, they use a different, in the code, their B bar is delta B, while here somewhere it is somehow more sophisticated. But anyway, you're absolutely right. It's because of the starting point, which is a differential equation, and the solution to that when you discretize it, that you get to a form that actually works because of this decaying phenomena. And also it self-normalizes itself. So every time you decay the memory a little bit and you add a bit of the input, and they go, they kind of in a normalized fashion. So some point in the paper later on, they have a theorem and they show how, they simplify the thing and show that how it's very similar to the forget and, the two gates that we see in LSTM. So that's how it works. So just wanted to say that.
So Vita, do you see how we're avoiding the vanishing gradient issue then? I still haven't seen anything that resonates with me as to why the vanishing gradient doesn't apply.
I think because it is well formed, the decaying thing, the EXP of delta A, and that EXP, the thing that you have in the EXP, like in the, if you look at the code, they have some SILU or maybe soft plus. They have a soft plus after the delta. So they force delta to be positive and A is negative and something like that. So the EXP that you have is EXP of a negative number. So all these A bars, when they get multiplied by each other, they get weaker and weaker and weaker. So what's the relationship between that and backpropagation of gradients? I mean, they are going to die off. I mean, so sorry, I'm not quite familiar with the names yet, but the other gentleman said, Ted said, that they are going to vanish, by the time you get after, 100,000 tokens to the first token, that token is going to get very small gradient from a token which is 100,000 away from it, but it's still going to get gradients from tokens who are closer to it. So, it's still going to train. And also the network, like other networks, they have normalization in other places, not necessarily inside this SSM thing, but it's very well formed. Again, it's an RNN that is conditioned and initialized very well. So again, if you look at the code and also in the paper, they say that they pay a specific attention to initializing the A matrix. It's not like the S4 or the hippo thing, but still they pay attention that, the elements are, I don't know, positive or something.
So is your answer somewhat quantity and numerically specific, meaning that by well-formed, you mean selected specifically to not propagate to zero? There's some mechanism by doing that?
So
or at least not so quickly. How about that?
So
you cannot avoid it, right? I mean, it's still going to happen, but in terms of numerical stability, at least, I think it's better well-formed or something.
Okay.
Right.
That's
So
why
there's two problems that you don't want, right? You don't want your hidden state itself
to explode
or vanish.
Exactly. Right.
Okay, that's the most important thing, right? If you just randomly have a formula and you say my hidden state equals this times my previous hidden state plus that, it could just go 1, 1.01, 1.1, 1.5, 2, 4, 8, boom, and explode, or it could go the other way. and it
Right.
can go 0.99, 0.9, 0.8, and then go to 0. So if you do that, then you're like really, really in deep trouble, because
Here,
your
right.
hidden state has vanished, let alone your gradients on the hidden state, because the
Right.
gradient on
Same
a
thing.
0 hidden state is bupkis, right? In this case, what we're saying, it's well formed, and so your hidden state is going to remain stable. But it is true that the more recent tokens are going to contribute a lot more to the gradient than the thing 100,000 steps ago. And
Right.
that's appropriate. That should be the case, right? Like if
Right.
you're saying the most recent words are the boy threw the, those words are going to contribute a lot more to next token prediction and error than the thing you said 100,000 words ago. Right? So logically, it should have a very minimal impact
That's
on.
often true, but not always true. It may be
I'm
that
not
the first thing you said was important. You are a helpful assistant AI. You want to remember forever. you
Yes.
know.
Yeah.
Yes.
So
The reason I asked the question about the reformulation of A to be I plus something is that the gradient problem, we solved that in deep CNNs through the skip connection, right? The residual connection.
But
And
you
you
know,
see them in transformers as well. And I was just wondering if that is somehow part of this formulation
so
that helps with the gradient, with the vanishing gradient.
so the
Or
vanishing
exploding.
gradient, you know, like what happens, I mean, what used to happen was that because of bad initialization, or because of, you know, they hadn't invented normalization yet, or dynamics of training was bad. So, you know, it's not like, you know, you had the state machine in the, you know, the RNNs were bad themselves. The dynamics of training, how, you know, loss was going low and how you were going down, you know, the gradient descent itself would become unstable and bad. And that was the, you know, that was what they meant by vanishing gradients, because the gradients were vanishing or exploding. So training was not happening. So it wasn't like, you know, there's a little bit of subtle.
Yeah. So,
but if
so
I have
along those lines, when you train a real RNN model, you not only have the RNN at X many time steps, but you typically build a deep model. So you have multiple layers of RNNs. Okay. So the residual connections are what we have between layers. You have those in a ResNet CNN, you have those in a transformer, and you do have those, although it's not obvious from looking at the diagrams, you do have those in Mamba as well. So if we build a layer of Mambas, and then we have 24 of them, there's residual connections between each one, just like in a transformer. Okay. So you get rid of the training problems of diminishing gradients in this direction, in the layer direction. But yes, I do think that it is still going to be true that even if you have whatever well-conditioned hidden states, the further back you go, the smaller it's going to contribute from the current token. But
so may I also bring the attention to this paper? You know, so there is definitely, you know, the theory that Vida is pointing out too. If you look at the last paragraph there, which spills over to the next page, they do talk about how and why this works better for SSMs regarding the vanishing gradient problem. So there's a long line of work on orthogonal RNNs, which are motivated by constraining the A bar transition matrix to be orthogonal or unitary in order to control its eigenvalues and prevent the vanishing gradient problem. Now, I don't understand all the math behind it, but I'm assuming that there are some works that were done even on the RNN side, similar to this mechanism.
You want the eigenvalues to be negative, I think.
Well, you really want them
to
to be close
exactly
to
one.
1 or -1, because that way it doesn't explode. But
yeah, I mean, not too big, too negative, close to 1, and yeah, but negative.
Yeah.
Yeah.
Very close to 1.
Yeah, it should be like 0.9 something, and then on a higher level, simpler. So Dave, thanks for pointing out. So Roger, you might want to read Appendix B3.
Yeah.
And see if that can help with a little more. They do mention the vanishing gradients a little bit. They do an ablation to say which is the most important thing, letting B bar be dependent on, but no, be dependent on the input, letting C be dependent on the input, or letting delta be dependent on the input. Okay, and when they do this ablation, table 9 is the results. If you look at it, you'll see that the biggest change in perplexity comes from letting delta change. Okay, and so let me find where they actually talk about this. So it says, showing that delta is the most important parameter due to its connection to RNN gating. And so I may need to find earlier where they say exactly, I think what Vita was saying is that delta is considered sort of akin to the forget logic.
You can search for theorem. I remember they had made it a theorem or
Yes.
something.
And so there is an intuition. I'm not sure if this is really a mathematically correct intuition. It's a nice, pretty one. But so by letting delta, if it's the forget parameter, by letting it depend on your input, you could maybe say that, like, when I see a word like the that tends not to be all that meaningful, then delta might be a very weak forget. Okay, just keep most of your prior state and add a little bit from the current input the. But for most other words, you might expect delta to be a bigger forget signal because you should pay attention to the new word that I'm just giving you. So when I give you the word dog or when I give you the word bank, you should forget your old state a little more because you need to make room for what I'm saying now. I don't know if that's a really great intuition, but they do say elsewhere in the paper that this selection concept is tied to how much you want to pay attention to the latest input. And so if you're going to pay attention to it and you have a fixed amount of state, that means you have to forget more of your previous state. Fundamentally, that's sort of the zero-sum logic, right? And so that's why they hypothesize that delta would be the most important of them to let vary. And then they do the ablation in table 7 that shows that, in fact, it is the most important. It doesn't directly tie to vanishing gradients, but I wanted to tie back to what Vita said about like those dynamics.